Relative Gravity Lecture 3. The Thermodynamic Galaxy.
Galactic Thermodynamics Summary. Why this work is special. The study of galaxies has long been dominated by classical gravitational models, often treating them as passive structures bound by Newtonian and Einsteinian mechanics. However, this work challenges and expands upon these traditional views by integrating relative gravity with thermodynamic principles, revealing galaxies as self-regulating, energy-cycling systems rather than mere gravitational constructs. Key contributions. Reframing galactic dynamics. This paper introduces the idea that galaxies function as thermodynamic engines, where motion through cold space, rotational momentum, and gravitational impedance regulate energy balance over cosmic timescales. The black hole is a spatial induction engine, rather than merely consuming matter. Black holes play a fundamental role in energy redistribution, acting as heat reservoirs and maintaining galactic stability. The galactic Carnot cycle, by applying thermodynamic efficiency principles demonstrated as how galaxies prevent entropy-driven collapse by continuously recycling energy. Dark matter as gravitational impedance, instead of assuming an unknown particulate form. This work proposes that dark matter is an emergent property of spacetime that stabilizes galactic energy flows. Implications for universal evolution. The thermodynamic balance observed in galaxies suggests that the universe itself operates as a self-sustaining, cyclic system, challenging heat-death models and suggesting a perpetual energy cycle. Why this is special. This work offers a paradigm shift in understanding cosmic structures by unifying thermodynamics with gravity, something rarely considered in mainstream astrophysics. It provides a foundation for future studies that could redefine the mechanisms of energy conservation in cosmic structures, the role of black holes beyond singularities, the true nature of dark matter and cosmic stability. By treating galaxies as living, dynamic systems, this research moves beyond static models, offering a functional, predictive framework that could revolutionize both astrophysics and cosmology. By Orion Carl Daly 3. Aka. Essay on Relative Gravity to Describe the Mechanics of the Universe 1. Introduction. The Self-Regulating Cosmos. The structure and dynamics of a galaxy are far more than just gravitational interactions between celestial bodies. Rather, galaxies function as self-sustaining thermodynamic systems where motion, temperature gradients, and gravitational mechanics work together to maintain energy balance. This view is fundamentally supported by relative gravity, which extends beyond traditional Newtonian and Einsteinian models by introducing the concept of gravitational impedance, a dynamic interaction between light and dark matter that regulates energy distribution across galactic structures. Additionally, thermodynamic principles from classical physics provide a framework for understanding the continuous flow and conservation of energy within these celestial systems. A central question arises: how do galaxies maintain their energy and structure over billions of years without collapsing or dispersing into thermal equilibrium? The answer lies in several interdependent mechanisms. 1. Motion against cold space. According to relative gravity, hot celestial bodies moving through cold space experience a self-sustaining thermodynamic cycle, where kinetic and thermal energy are conserved through gravitational interactions. Without this motion, celestial bodies would eventually lose energy and reach equilibrium, disrupting galactic stability. 2. Black holes as energy regulators. The supermassive black hole at the galactic center acts as both an energy sink and a distributor, influencing the galactic energy cycle much like a thermodynamic engine. This perspective aligns with relative gravity's concept of black holes as active energy regulators rather than mere gravitational sinks. 3. Gravitational and thermal energy exchange. Traditional physics suggests that galaxies should gradually lose energy and disperse, but observational data contradicts this. Relative gravity provides an alternative explanation, suggesting that gravitational impedance and harmonics create a self-regulating energy system, preventing galaxies from succumbing to entropy-driven heat death. By integrating relative gravity with thermodynamics, proposed is a unified model where galaxies are not passive systems governed solely by gravity but active, self-sustaining structures operating within an interconnected energy cycle. This paper will explore how these fundamental principles shape galactic motion, stability, and energy conservation over cosmic timescales. By Orion Carl Daly 4. Galactic Thermodynamics 2. The Purpose of the Black Hole. Galactic Energy Regulation. At the heart of most galaxies lies a supermassive black hole, which acts as both an energy sink and an energy distributor. Contrary to classical views that depict black holes as purely consumptive entities, relative gravity suggests that they play an active role in regulating energy balance across galactic structures. 2.1 Heat reservoir and energy recycling. The black hole's accretion disk collects matter, generating intense gravitational pressure and frictional heating. leading to the emission of vast amounts of thermal energy, radiation, and high-energy particles. Relativistic jets, a product of the black hole's magnetic and rotational dynamics, redistribute energy outward, influencing stellar formation, galactic wind patterns, and the intergalactic medium. This cycle of energy absorption, redistribution, and release functions analogously to a thermodynamic heat engine, where input energy is processed and redistributed to maintain dynamic equilibrium. 2.2 The black hole as a thermodynamic engine. Black holes operate similarly to a Carnot cycle, where the galactic core acts as a high-energy reservoir. The outer galactic regions and intergalactic space function as the low-energy reservoir. The black hole facilitates the movement of energy between these states, maintaining galactic thermodynamic stability. Entropy regulation. The black hole plays a crucial role in controlling entropy by regulating the dispersal of energy. The equation governing this entropy balance can be represented as case 4 where SBH is the black hole entropy, K is Boltzmann's constant, C is the speed of light, J is the gravitational constant, H is the reduced Planck's constant, I is the event horizon area. By Ryan Carl Daly 5. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. This equation illustrates that as a black hole accumulates mass, its entropy increases proportionally. But the simultaneous release of radiation and energy prevents an unbounded entropy rise, maintaining cosmic balance. Gravitational energy recycling. This regulated cycling mechanism prevents local thermal collapse and allows energy to be continuously exchanged between different galactic regions. 2.3 Expanding the role of relativistic jets in galactic energy flow. Jet dynamics and galactic magnetic fields. Relativistic jets, propelled by strong magnetic fields, amplify large-scale galactic magnetism. The interaction between jets and the interstellar medium generates turbulence, influencing large-scale cosmic energy redistribution. Impact on star formation and the intergalactic medium. Jets inject high-energy particles into the intergalactic medium, preventing excessive cooling and regulating star formation rates. The energy dispersion from jets alters the thermal equilibrium of galactic halos, impacting the balance between stellar birth and galactic evolution. 2.4 Gravitational impedance as a regulatory mechanism. Instead of dark matter being a particulate entity, relative gravity describes it as an impedance factor in space-time, moderating the dynamics of gravitational interactions. Energy redistribution and stabilization. Energy does not simply disappear into the black hole, rather, gravitational impedance resists immediate collapse, creating an oscillatory exchange between mass energy, accumulation, and redistribution. Synchronization with galactic rotation. 2.5 Black holes do not exist in isolation, they synchronize with the galactic plane's rotation, ensuring energy flows are proportionally distributed. The equation governing the synchronization is omega bh approximately k omega galaxy, where omega bh is the black hole's angular velocity and omega galaxy is the angular velocity of the galaxy itself. This relationship ensures that the energy regulation of the black hole aligns with the broader galactic dynamics. Dark matter is a stabilizing factor, rather than acting as a form of unseen mass. Dark matter, when viewed as an impedance effect, prevents runaway gravitational collapse by balancing the energy-matter relationship across cosmic structures. This stabilizing function prevents galaxies from spiraling into chaotic disintegration. By Ryan Carl Daly 6. Galactic thermodynamics. Thus, the black hole is not merely a final destination for matter and energy, it actively redistributes and regulates energy across the galaxy, ensuring dynamic stability and sustained structural integrity. By Ryan Carl Daly 7. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe 3. The Galactic Carnot Cycle. Motion against cold space. Galaxies do not exist in isolation, they operate within the broader cosmic framework, where the motion of celestial bodies through cold space generates a thermodynamic interplay that sustains their energy and structure. Relative gravity extends traditional views by positing that this motion is crucial to maintaining thermal and kinetic equilibrium across cosmic scales. A fundamental feature of galactic stability is its ability to retain and recycle energy over cosmic timescales. Unlike isolated thermodynamic systems that eventually succumb to entropy, galaxies sustain themselves through continual motion and interaction with surrounding cosmic conditions. This motion ensures that energy is exchanged efficiently across various galactic layers, preventing total dissipation into cold space. Kinetic energy and thermal energy exchange. Celestial bodies moving within a galaxy generate heat not through friction, but via their interactions with gravitational fields and radiation emissions. These energy interactions contribute to localized flux variations that keep the system dynamic. The process aligns with relative gravity's view of gravitational impedance, wherein energy transfers are moderated by the surrounding spacetime medium. This motion is critical for preserving a dynamic temperature differential, ensuring that heat does not instantly dissipate into entropy. Deepening the thermodynamic cycles. To further refine our understanding of galactic thermodynamics, we must analyze the energy transformations within galaxies as a structured cycle. The galactic Carnot cycle framework, much like classical thermodynamic cycles, galaxies operate through a regulated energy exchange between high and low energy reservoirs. The galactic core TH serves as the high-temperature energy source, where intense radiation and black hole activity generate immense heat. The outer galactic regions TC act as the low-temperature sink, gradually radiating energy into intergalactic space. The movement of stellar bodies between these regions functions as a cyclic engine, ensuring energy retention without dissipation into equilibrium. Efficiency of energy retention. The efficiency of this thermodynamic cycle is determined using E equals 1 to CTH. This equation indicates that the greater the temperature differential, the more effectively energy is maintained within the galactic system. By Orion Carl Daly 8. Galactic Thermodynamics. Heat redistribution across galactic layers. The interaction between rotating stellar populations, interstellar gas, and cosmic radiation creates an evolving energy cycle that prevents uniform cooling. The combination of gravitational interactions and energy transport within a galaxy helps establish a self-sustaining equilibrium. If motion stops, energy is lost. According to thermodynamic principles, an object in motion maintains its internal energy relative to its surrounding conditions. If a celestial body were to come to rest, it would gradually radiate away its internal energy, reaching thermal equilibrium with the intergalactic background temperature. This principle highlights the necessity of continuous motion for maintaining galactic energy systems, reinforcing that motion against cold space is an essential thermodynamic requirement for galactic regulation. Rotational momentum as a self-sustaining mechanism. A galaxy's rotational momentum functions similarly to a flywheel, where conserved angular momentum sustains its structural integrity. Each celestial body within the galaxy contributes to this vast, interdependent energy cycle. The principle of angular momentum conservation prevents abrupt energy loss and maintains long-term galactic stability. This self-reinforcing cycle is not merely a mechanical necessity, but a thermodynamic imperative. Without it, galaxies would either collapse inward or fragment under their own gravitational forces. Multi-phase energy exchange within galactic structures. Beyond simple rotational dynamics, multi-phase energy exchange plays a significant role in galactic sustainability. Energy does not remain in a single form but transitions between stellar cores, nuclear fusion generating intense radiation and heat, interstellar gas acting as a thermal medium for energy diffusion, cosmic radiation releasing excess energy into the larger cosmic framework. This multi-phase interaction ensures that galaxies do not reach thermodynamic stagnation, but instead cycle energy dynamically across various spatial and temporal scales. By Orion Carl Daly 9. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Gravitational impedance as a heat buffer. Traditional astrophysics often attributes galactic stability to dark matter as a missing mass component. However, relative gravity proposes an alternative explanation. Gravitational impedance acts as a heat buffer, moderating energy diffusion across the galaxy. Rather than being an unseen particulate mass, dark matter may instead represent a property of spacetime that stabilizes energy transitions between large-scale structures. Thus, the galactic Carnot cycle, as supported by relative gravity, provides a framework where motion against cold space ensures the continuous exchange and regulation of energy, preventing the inevitable dissipation into entropy. Galaxies sustain themselves not through an isolated gravitational force alone, but through the thermodynamic balance of energy exchange across their rotating structures. By Orion Carl Daly 10. Galactic Thermodynamics 4. Galactic Stability and Self-Regulating Systems. The stability of galaxies over cosmic timescales is a result of intricate balancing mechanisms that operate at multiple scales. Traditional astrophysics attributes galactic stability to gravitational interactions and dark matter, but relative gravity provides a more comprehensive view, one in which gravitational impedance, energy cycling, and thermodynamic regulation play crucial roles in sustaining structural integrity. Galactic stability and self-regulating systems. The stability of galaxies over cosmic timescales is a result of intricate balancing mechanisms that operate at multiple scales. Traditional astrophysics attributes galactic stability to gravitational interactions and dark matter, but relative gravity provides a more comprehensive view, one in which gravitational impedance, energy cycling, and thermodynamic regulation play crucial roles in sustaining structural integrity. Galaxies are not static, they continuously evolve, exchanging energy with their surroundings while maintaining equilibrium through feedback loops that prevent both collapse and dispersion. This self-regulating behavior suggests that galaxies function as dynamic systems, where energy is not merely lost but reprocessed in a manner that sustains motion and structure. Gravitational resonance and harmonics. Resonance as a structural stabilizer. The spiral arms of galaxies exhibit behavior similar to resonance patterns seen in vibrational physics, where energy distribution follows harmonic wave structures. Dark matter is gravitational impedance. Instead of being an independent substance, dark matter may act as a form of gravitational impedance, ensuring the orderly motion of galactic components and reducing chaotic dispersion. Intergalactic influence. Neighboring galaxies and cosmic structures exert gravitational forces that contribute to resonance stability, reinforcing the galaxy's overall self-regulating behavior. Standing waves and galactic structure. Energy distribution mechanisms. Galactic structures exhibit standing wave behavior where density waves propagate through the disk, sustaining the long-term pattern of spiral arms. Thermodynamic balance. These standing waves act as natural conduits for energy redistribution, preventing excessive buildup in one region and allowing for a balanced thermodynamic state. Self-sustaining motion. The interaction of these waves with stellar populations and interstellar matter generates a self-reinforcing cycle of motion and energy exchange. Interplay between expansion and contraction. Black holes as energy regulators. At the core of most galaxies lies a supermassive black hole, which acts as an energy sink, balancing expansion forces with gravitational attraction. By Orion Carl Daly 11. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Stellar formation and radiation. While black holes pull in matter and energy, stellar processes such as nuclear fusion and supernova release energy outward, creating a counteracting force that maintains equilibrium. Galactic feedback loops. This balance between contraction and expansion ensures that galaxies do not collapse under their own gravity or dissipate into the cosmic background. Thus, a galaxy operates as a self-regulating feedback loop, where energy is not lost but continuously cycled and reprocessed through gravitational impedance and thermodynamic balancing mechanisms. By integrating these principles, achieve is a deeper understanding of why galaxies persist for billions of years without undergoing total collapse or dispersal into thermal equilibrium. By Orion Carl Daly 12. Galactic Thermodynamics 5. Cosmic Evolution and the Universal Thermodynamic Framework. The self-regulating nature of galaxies suggests that the universe itself may follow similar thermodynamic principles. If galaxies can sustain stability through energy recycling and gravitational impedance, then on a larger scale, cosmic evolution may be governed by universal thermodynamic feedback loops that maintain order across vast expanses of space-time. From the perspective of relative gravity, the universe does not expand indefinitely nor approach heat death, but instead undergoes cyclic energy transformations, ensuring perpetual regeneration of matter and energy. 5.1 Galactic motion as a heat exchange mechanism. Intergalactic space as a cold reservoir. Just as the galactic Carnot cycle operates by maintaining temperature differentials, intergalactic space serves as a vast cold reservoir that absorbs radiated energy from galaxies. Galaxies as heat engines. The dynamic processes of galaxies, stellar formation, supernova, and black hole activity function as heat sources, driving cosmic energy redistribution. Relative gravity and heat flow. The transfer of energy between these systems follows predictable paths dictated by gravitational impedance, ensuring no system becomes completely isolated. 5.2 Universal energy recycling. Cosmic background radiation as a relic of prior cycles. The energy signature observed in the cosmic microwave background CMB may not be a relic of a singular Big Bang, but instead, the thermodynamic residue of previous cosmic cycles. Quasars and active galactic nuclei as energy redistribution centers. These energetic sources inject radiation into the intergalactic medium, maintaining an equilibrium that prevents thermal collapse. Energy flow between galactic clusters. Large-scale cosmic structures participate in gravitational wave interactions, enabling long-term stabilization of energy distributions. 5.3 A multiversal perspective. Cyclic universe model. Rather than existing in a state of constant expansion, the universe may undergo oscillatory phases where energy density fluctuates in a manner analogous to a cosmic breathing cycle. Inter-universal interactions. The exchange of energy across universal boundaries, perhaps via manifold intersections, could explain anomalies in cosmic structure and dark energy behavior. By Orion Carl Daly 13. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Quantum fluctuations as the seeds of cosmic regeneration. Small-scale fluctuations may serve as the foundational elements for new cosmic structures, bridging the micro and macro scales of universal evolution. By treating the universe as a self-regulating thermodynamic entity, we can move beyond traditional cosmological models and into a realm where energy conservation, cyclic processes, and gravitational impedance define the overarching mechanics of cosmic evolution. By Ryan Carl Daly 14. Galactic Thermodynamics 6. Conclusion: a new understanding of galactic and cosmic regulation. For centuries, galaxies have been viewed as mere collections of gravitationally bound objects, passively moving through space. However, this perspective does not fully account for the intricate energy dynamics that sustain galactic structures over billions of years. Instead of being solely governed by gravity, galaxies function as self-regulating thermodynamic engines where motion, gravitational impedance, and black holes collectively stabilize and balance energy flow. By integrating relative gravity with thermodynamic principles, we establish a more comprehensive framework that fundamentally redefines cosmic regulation. Black holes as energy regulators. Black holes are not mere sinks, but active moderators of energy balance. They function as galactic energy hubs, redistributing mass energy and preventing runaway thermodynamic collapse. Motion through cold space as a thermodynamic driver. The interaction between moving celestial bodies and the surrounding vacuum maintains a continuous thermodynamic cycle, ensuring the sustainable recycling of energy. Galaxies as self-sustaining systems. The conservation of angular momentum, gravitational impedance, and cosmic feedback loops collectively prevent both runaway expansion and uncontrolled energy dissipation, maintaining a state of dynamic equilibrium. This integrated perspective provides a more predictive and explanatory model of the cosmos, one that challenges the traditional notion of an eventual heat death. Instead, it suggests that the universe operates as an infinite cyclic system in which energy, structure, and motion perpetuate through continuous regeneration and transformation. By viewing cosmic evolution through this expanded lens, we move beyond static models toward a unified, thermodynamically driven understanding of the universe, one where equilibrium and energy flow sustain structure across infinite scales of time and space.